Last time we were talking about randomized algorithms. At a high level, this idea of introducing randomness into the computation in order to avoid the worst case, basically. The perspective is that there's some adversary that knows about your algorithm and is trying to make it run as slowly as possible. If you make your algorithm unpredictable by randomizing, it becomes difficult for that adversary to put you into that situation. Now, I should say, in the real world, there often isn't an explicit adversary, but there are patterns, and there's sort of natural structure. So, for example, although we won't be studying it in this class, the quicksort algorithm, which many of you are familiar with, right, picks a pivot and then splits according to the pivot. And if you do this deterministically, a natural thing to do is take the first element as the pivot and use that as the splitter and then recurse. And that often works fine, but if the input happens to be sorted, then using that deterministic strategy makes quicksort take quadratic time. If you instead pick a random pivot, then a sorted input is still likely to run quickly with quicksort. So there what's happening is that randomization is disrupting the patterns that make your algorithm perform poorly, which can be patterns that arise in practice. So like sorting a sorted list is remarkably common, actually. So you don't want an algorithm that does badly on a sorted input. Okay? And so we're using randomization in hashing. And again, a lot of times you could say, I'll just pick a deterministic hash function and it will work. But the problem is that for any specific hash function, there are inputs on which it will perform badly. And even if you don't have an adversary trying to pick the worst input, the worst set of keys for you, there may be some hidden pattern that gets hit by the hash function that you choose to use. So if instead you randomize, you avoid running into those hidden patterns. We did say, however, that formally at least, no one function can always be good. Right? Because of the pigeonhole principle, you can always find a set of keys that all hash to the same bucket and make collisions and make everything collide. So instead, we look for what's called a hash family, right? A collection of hash functions. And the sort of most basic thing you could ask for is that for any particular input, there should be a good hash function, right? We're actually generating hash families where most of the hash functions are good for any particular input. Okay? In particular, we looked at what's called two-universal hashing, which was developed by Carter and Wegman. And I introduced the main idea of it last time, right? I said that if we assign keys to random buckets, right, then the expected number of collisions for item I is equal to the expectation of the sum of indicator variables, right? This is the indicator for I colliding with J, which is equal to the sum of the expectations, which is equal to the number of items, which is n minus I itself, times the probability of a specific item colliding, which is 1 over s. And so we just bound this by n over s. Okay? And so as long as the space is significantly larger than n, the expected number of collisions is quite small, and that expected number of collisions is the time it will take you to do a lookup for the item, and actually also the time it will take you to find the item in order to delete it. You can always do insertions in constant time if you are storing things in a linked list, because you can always put the item in right at the front of the bucket. You don't have to look at everything else. And so this used a couple of the sort of key ideas from probability that we will be using. And so I figured I would put those in a corner of a board just for general recollection. One is this idea of indicator variables. And the second is linearity of expectation. Okay, we'll have a few more coming. So we know that a random function works well, but we talked about the problems with random functions. And so we observed that in this analysis, pairwise independence is sufficient. Right? The Cij indicator variable depends only on the placement of I and j. And so as long as those two placements are independent, it doesn't matter what happens with the other items. And so we just need pairs of items to have independence. And so we defined this idea of a hash function where we said choose a p. And I'm going to make, and it's important that p be larger than m. And just to put a bound on it, I'll make it smaller than 2m, which is prime. And then I defined the hash family, h sub ab, which is defined where I specify that h sub ab of x is equal to ax plus b mod p. And what I showed you last time was that over random uniform choice of AB, the function, the values HAB of x and HAB of y are independent, right? For as long as x is not equal. Sorry, let me leave room for my list of probability things. We say HAB of x and HAB of y are independent when x is not equal to y. Okay. Remember, m is the largest number in our key space, so x and y are both smaller than m, and that's important. Okay. And so this gives us pairwise placement, pairwise independent placement of all the items that we are hashing. Yes? And I won't repeat the proof. We did that last time. It was a little bit of matrix algebra over the field ZP, right? Right? That's what we're relying on, is that ZP is a field, which means you can do division. And that means that we can solve this matrix inequality and find that there's a unique solution to it, which is what gives us the pairwise independence. Okay? Now, I want to point out something a little bit weird here, right? Notice that with probability 1 over p, a is equal to 0, right? Now, if a is equal to 0, what is your hash function going to do? Yes?
Lots of collisions, everything goes to the same place.
Everything will go to the same bucket if a is equal to 0, right? So that seems like a really terrible idea, to have a equals 0. And two things to observe about. First of all, bad as it is, it doesn't matter for our analysis, right? The whole idea of a randomized algorithm is that there is a small chance of something going really wrong, but usually everything is great. Okay? There are other kinds of algorithms, we'll see one actually called Las Vegas algorithms, where you can guarantee that nothing goes wrong, even though it's randomized. But this is what's called Monte Carlo. There's a chance that you get into a lot of trouble. Okay? In a sense, this is the trade-off you make from deterministic algorithms. Right? With deterministic algorithms, there are a few inputs that make things go terribly. Right? And so again, your adversary or patterns in nature could result in your hitting those inputs. But with randomized algorithms, instead of there being a few bad inputs, there are a few bad there's some bad luck, right? There's a small chance that things go really badly with your random choices. So you're kind of smearing out, instead of having a specific bad input, you put a little bit of badness on every input. Okay. So if A equals 0, everything collides, and that's bad. Okay. Now, if you notice this, you might say, well, what I should do is I should exclude 0 as an option for A. Okay. And that actually will work, right? But you won't have you won't have sort of the right kind, the uniform pairwise independent distribution anymore. If A cannot be 0, it slightly changes the probabilities of things colliding, and it slightly changes the joint distributions. It doesn't change them in a way that makes the results not work, but it does change them in a way which makes it much harder, much messier to analyze. So we're just going to live with this because it keeps the analysis elegant. Okay? In practice, you might want to avoid that problem. Okay? So if we do this, we end up with pairwise independent positions, but we have to be a little careful here. We still don't have a workable hash function, right, for what we want, because what is the range of this function? Yes?
P.
The range of this function is p, which is something a little bit bigger than m, right? What do we want the range of the function to be? What are we hashing into? Yes?
S.
We want it to be S, right? We want to get an S space. If we were going to put things into M space, we wouldn't need to hash at all. We would just use an array, right? But M is much bigger than S, so we need to squash things into S space. How are we going to do that? Well, the simplest way imaginable, we'll just do everything mod S when we're done. Okay. Now, if we're going to mod S after all, why don't we just mod S? Why shouldn't our hash function just be, h of x equals x mod S? Right? That would work as a hash function. Yes?
You kind of want to shuffle the elements around. If you just do mod S, then any adversary can easily know what elements are going to end in the same bucket.
Right. What elements are going to end up in the same bucket? Yeah?
There are multiples of S, or divisors of S, that will lead into many things close to the same thing. Maybe
Exactly. Right. All the multiples of S will end up in bucket 0, and basically any two items that differ by exactly S will end up in the same bucket, right? And this is the kind of pattern that you would expect is going to show up in nature, right? Evenly spaced items. So that might be a terrible idea in practice, okay? Now, so that would be a terrible hash function in practice, either because of an adversary knowing about it or because of the patterns in nature. Why is it fine to tack it on here? Yes?
You want to move the stuff around?
Exactly. This inner hash essentially turns all the keys random, right? And goes to what you, again, when hashing is taught in elementary algorithms, we say, assume the keys are random, right? Or assume the hash function is random, right? And once the hash function is random, everything is great, per the analysis that we've already done, right? So this makes things random. And once the keys are random, you don't have that pattern of things spaced out by exactly S. And so it's fine to go mod S once you have random keys. Okay? Now we do need to be a little bit careful. Okay? I claim that this hash function will not uniformly distribute the keys. Right? Why is that? I say it will not quite uniformly distribute the keys. Yes?
Because if P is prime, then M is not divisible, P is not divisible by M, and so some remainders occur more often than others.
Well, so it's not about M, because whether
I mean, sorry, S.
right, S, exactly. So the point is that we're taking, this inner function maps the items to be numbers between 0 and P, uniformly at random, right? But then, these numbers that range between 0 and P minus 1, when we go mod S, they're not evenly distributed among the range from 1 to S. Because if they were, it would mean that S is a divisor of P. Right? That's the only way to get a uniform distribution. But P is prime, so it doesn't have any divisors. So some of the buckets are going to get one more item from the range than other buckets, right? And that's basically what's going to happen, is that buckets 0, 1, 2, 3, and so on are going to have ceiling of P over S items, and then at a certain point, your later buckets are going to have floor of P over S items, right? So there's a slight difference, but remember that P is very large, right? Bigger than M, whereas S is very small, or polynomial at least. And so this difference is negligible, and I'm not even going to worry about it, right? So not quite uniform, but close enough that it's just an epsilon term in this number of collisions analysis. Okay. As long as P is significantly larger than S. Okay. So now we do have an actual hash function that goes from your key space of 0 to M into your hash space of 0 to S minus 1. Let me point out one other interesting aside. We proved that the expected number, or actually, one other thing first. Notice that this hash family is small. Right? It only has P squared functions in it. So that's one of the things that was important. That means that we can store the hash family by just storing A and B. So it's easy for us to remember which hash function we're using, and we can compute it in constant time. So the hash functions in this family meet our goals for hash functions, that they're easy to represent and quick to compute. Okay? And they provide this guarantee of expected order 1 collisions for lookups. Okay? So now a little aside, expectation is very nice, right? That's always the first thing you want to use to understand a distribution. But sometimes theoreticians, computer scientists want more. They want to talk about the probability of a bad event, right? It's very nice to know that on average, you're going to have order 1 collisions, but what are the odds that you'll have more collisions, right? This might be of importance to you if you're developing a real-time application where you really need to know that you're not going to have a lot of collisions, right? I mean, it might be fine if there's a 1 in a billion chance of having lots of collisions, but if there's a 1 in 10 chance of having lots of collisions, that might be something to worry about, even if the expectation is small. Okay? So you can talk about tail bounds, right? Bounding the probability that things get very far away from their expectations. And I will just mention this as an aside. If you want to sort of learn more about this, you can take my randomized algorithms class, which will be offered at some random time in the future. The expected number of collisions is less than or equal to n over s, which is less than or equal to 1 if s is bigger than n. And obviously, we're going to need to use n space, so we should take s bigger than n. But what can we say about the maximum load? The load is just the number of collisions in a bin. Right? So what's the biggest bin in your hash table? Okay. And we can also ask about the expected maximum load. So on average, what's the biggest load you're going to see? So sure, for a single item, looking it up takes constant time, but it would be interesting if we knew that some item was slow most of the time, right? Or that in expectation, there were some slow items, which is about the max load as opposed to the average load, right? Now, is this equal to just, should we just take the maximum outside of the expectation? Well, sadly, no. We have linearity of expectation, but we don't have maximality of expectation. You can't just pull out a max, right? And so, for example, there's this well-known fact that for what's called balls and bins, if you put n balls in n bins, then the expected maximum load is theta of log n over log n. And that's theta. So yeah, the max load isn't very big. It's less than log n. But there is, you're quite confident that you are going to see a load which is bigger than a constant, but is approaching log n. Okay. And in fact, this value holds with high probability. Okay? That is, it is extremely unlikely that the load will be bigger, but it's also extremely unlikely that the load will be smaller. Okay. Now, for two universal hash functions, the story is worse because, right, large loads arise from the interaction of many items, all landing in the same bin. And pairwise independence doesn't really give you a lot of control over groups of items, right? It's only addressing pairs of items. So you can prove, using what's called the Chebyshev bound, that the probability that the max load is bigger than the square root of n is at most 1 minus 1 over n. Okay. So it is unlikely for the maximum load to be more than the square root of the number of items. But that's way worse than for a truly random function. Okay? And in fact, in a real display of theoreticians' perversity, there's a whole paper where a bunch of theoreticians worked to create a pairwise independent hash function. And it does pairwise and nevertheless, it almost guarantees that the maximum load will be square root of n. Okay? So there exist two universal families where this is almost always true. Okay. Now, I don't think anybody has proven whether or not it is true for this pairwise independent family, but you can generate other pairwise independent families using matrix operations, or again, doing some weird stuff. You can create another two universal family where you're pretty much guaranteed to have a load of square root of n. Now, let's think about it. Suppose that we do have a square root of n load in some bucket. Does that destroy our expectation analysis? Well, no, right? If I have root n items in a bucket, it means that root n of the items are going to take root n time for a lookup, which is a total of n time being spent on those root n items, but that only happens with probability 1 over n, so in expectation, it's still constant. Okay? If you had more than root n items, if you had n to the 2/3 items in a single bucket, that would start to mess with your constant time expectation, but square root of n does not. Okay? So that's just an aside. Like I said, we'll fill that in if you take randomized algorithms. One other aside, this is the last one, let's talk about the dynamic case. What if you're doing insertions and deletions? Okay. So this whole analysis said, let's fix a set of items, and let's understand the expected lookup time for the items in that fixed set after we've hashed it. Okay? But in a typical hash table, you'll be inserting and deleting items, and you want to know what is the lookup time for the current set of items. Right? And my claim is that the analysis is unchanged for a so-called oblivious adversary. And again, I'll fill in this more in randomized algorithms. If the adversary does not know what my choice of random hash function is, if you think about it, I don't actually have to choose the hash function in advance in order to analyze it, right? Instead, I can wait to look at the hash function until the adversary asks me to analyze the expected lookup time for the 17th operation. Right? So when I'm told to analyze the expected lookup time for the 17th operation, I'll say, well, what were the items in the hash table at the time of the 17th operation? I'm choosing a random hash function. Therefore, this analysis applies, and the 17th lookup takes expected constant time. Okay. Now, this changes if, after I generate my hash function, the adversary can look and see what it is. Right? If the adversary can look at my hash function and see what it is, they can make things arbitrarily bad for me using the same pigeonhole argument, right? They'll just find a bunch of items that all map to the same bucket, and they'll insert those, and my hash table will be terrible. Okay? But it's reasonable to assume in many cases, although not in cryptography, for example, that your adversary is not able to access your it's not a security, I should say. The adversaries can't access your randomness, and so this analysis is still valid even if you're inserting and deleting items. Okay. Any questions about that? Okay, so with really negligible work, negligible math, we were able to achieve expected constant time lookups. So since that was so easy, let me give us a more challenging objective. Suppose we want to have 0 collisions. Okay. We want to hash our items into a hash table so that only one item lands in any bucket. This is known as perfect hashing. Okay. We're given n items, and we want to hash such that there are no collisions. And if you think about it, right, this is really useful because instead of now having to talk about an expected time analysis, we can talk about worst case, right? If there are no collisions, then every lookup is order 1. No ifs, ands, or buts. Right? And so this is really important for real-time applications. It's also great for, storing data, delivering data, right? If you don't need a linked list, right, you can just put the items into the array, right? And you don't need all of the extra pointers and the weird mapping of storage, and you can keep your locality and things. So perfect hashing has some nice features. Can we do it? Okay. And so we want to define a perfect hash function, which is one of these hash functions that takes your items and gives you no collisions. And obviously, the perfectness of the hash function depends on what the keys are, right? You can't say a hash function is perfect by itself. It's perfect for a particular set of keys. And this is a lot more challenging than regular hashing because even a random function is going to have some collisions, right? Just by bad luck. So this wants to be a better than random function instead of just matching what random functions do. So, ideally, we would want to hash our n items into an array of size n. But for starters, let's try our same old hash function, but using more space. Okay? We already bounded the number of collisions for a particular item. Let's instead bound the total number of collisions when we do two universal hashing, which is just the sum over all pairs I and j of the collision indicator. And now let's look at the expected value of that total, where we can, of course, use the linearity of expectation and analyze it just as before, except that we're now summing over n squared pairs of indices, right? Sorry, n minus 1 squared pairs of indices, or more precisely, n choose 2 pairs of indices, right? And for each of them, the probability of collision is 1 over s. Okay? And so that is upper bounded by n squared over 2s. Okay. So, if we make s really big, this is close to 0, right? But it's not quite 0. I mean, if, for example, if we set s equals n squared, we get half a collision in expectation. Okay, but that's weird. You can't actually have half a collision, right? Either you have a collision or you don't have a collision. Okay. But I argue that this gives us a chance of having no collisions. Okay. In order to prove that, I'm going to pull out the third kind of trick the probability trick that we're going to be making repeated use of, which is what's called Markov's inequality. Okay. If you have a random variable which is non-negative, okay, then the probability that x is greater than any quantity t is at most the expectation of that random variable divided by t. Or another way that this is often written is that the probability that x is bigger than some quantity r times its expectation is at most 1 over r. Okay. And the proof of this, the intuition behind this is captured by a famous old television show called The Prairie Home Companion. The introduction to this show talked about Lake Wobegon, where the women are strong, the men are beautiful, and all the children are above average. Can that happen? I mean, not the strong women, beautiful men part, but can all the children be above average? No. How come? I mean, you feel bad for the children who are below average, but why do there have to be some? I mean, obviously none of them are here at MIT, but what was that? No one has to be below average. It's true. Everybody could be exactly average, right? But how come we can't have everybody above average?
Well, then the average would be larger.
Because then the average would be larger, right? The average is somewhere between the biggest and the smallest. It can't be below the smallest, right? It's a convex combination, right? And Markov's inequality just generalizes this idea, right? If, for example, you had more than a 50% chance of being bigger than twice the expectation, then the contribution of all of that, of all of those events would by themselves give you a larger expectation than the one that you're claiming. Okay? And so you can't have the probability that you're more than twice the expectation is at most a half. Okay. And I'm not going to prove that out in detail. Again, I think you've all seen it in 604.2. If you haven't seen it, sort of check it for yourself just so that you're confident in it. But let me add that to our list of really important things to remember in probability. Okay. So how do we use Markov's inequality here? To get from an expectation to 0 collisions. Yes?
We know that there's a like 50% chance that there would be no collision from the Markov inequality.
Exactly. Right? Just from setting the expected number of collisions to a half, right? The probability that we have at least one collision is at most a half, thanks to the Markov inequality. Right? And of course, if we don't have one collision, then we have 0, which makes us perfect. So we have our first perfect hash function. Just hash your n items to n squared space, and you have a good chance of having no collisions. Okay, a good chance is nice, but a good chance is not certainty. What if we want certainty? Yes? Repeat. Okay. If you don't succeed, try again. Okay. So we hash our items, we check for collisions. If we have a collision, generate a different hash function, right? And remember, these are all the HAB, these are the 2 universal hash functions, right? Nicely stored, quick to compute. We just keep computing one until we get no collisions. Okay. So this lets me differentiate. So actually, how long is it going to take us to find one of these perfect hash functions if we keep trying? Yes?
It could take arbitrarily long.
It could take arbitrarily long, right? Maybe we have such terrible luck that we just keep trying for an infinite amount of time, and we keep on ending up with imperfect hash functions. All right, so we can't talk about certainty, but what can we talk about is that the time it takes us is a random variable, and so it has an expectation, right? So let's talk about the expected number of tries. Can we bound that? It's 2, right? Or is it most 2? This is because the trials are a geometric distribution. Right? We keep trying where our probability of success is at least a half, and even if it's equal to a half, right, the expectation of that distribution is 2. Okay. So this is a really common transformation. You go from an algorithm that is guaranteed to be fast and might be correct, right? In this case, we're talking about the algorithm for finding a perfect hash function, right? So this is an algorithm that takes one hash function to compute, right? That you compute one hash function, has a 50% chance of success. You can switch over to an algorithm that is guaranteed to find you a perfect hash function and is probably fast, in that you probably don't have to try a lot of hash functions, but you might have to try a lot of hash functions, right? So this distinguishes what are called Monte Carlo algorithms. Fast for sure. correct, versus what are called Las Vegas algorithms, which are correct for sure and probably fast. It turns out you can go, we've now shown how to switch any Monte Carlo algorithm to a Las Vegas algorithm using this technique, which is called amplification, which is just the fancy name for trying over and over again until you succeed. Okay? So let me add that to our list of things to remember. That if you have an algorithm that has a certain probability of success, you could just keep trying that algorithm in order to improve its probability of success. And if you keep trying until you succeed, then you get a guaranteed successful algorithm. It just might take you more time. Okay. All right, so now we're in a good shape. We have this perfect hash function, but it's not really ideal because we're using so much space. So the first question I'll ask is, do we have to use this much space? What if we made S smaller than n squared? You know, our current analysis doesn't really say what's going to happen, or I mean, our analysis is based on some upper bounds. Maybe our analysis is weak. Maybe with even smaller space, we would still have a decent chance of getting a perfect hash function. What do you think? Is this tight? Well, let me frame it a way that you may have heard it before. Suppose that I'm trying to hash into, say, 365 buckets. And my method of randomization is by letting people be born at random days of the year. Okay? So the bucket you land in is your birth date. What can I say about collisions in that sort of situation? Like, you know, how many people can I hash into my 365 buckets before I start seeing some collisions happening? Yes.
Something like 23.
23. How does 23 relate to 365?
Square root?
It's the square. It's that square root. It's this s equals n squared relationship, right? So the birthday paradox says you can't improve on s equals n squared. That basically, once s is once n is, so let me turn it around. You can't improve on n equals root s because once n is sufficiently larger than root s, you start seeing collisions. And you may remember the proof of this, that basically, you know, your first item obviously won't collide with itself, but the second item has a 1 minus 1 over n chance of not colliding with the first item, and the third item has a 1 minus 2 over n chance of not colliding with either of the previous items, and sorry, these are s's. And you keep going down to 1 minus n over s, and this is roughly the probability of getting no collisions, right? But now we use my favorite approximation that 1 minus x is roughly e to the minus x. And so this is approximately e to the minus 1 over s minus 2 over s minus 3 over s all the way down to n over s. Right? And here on the top, we just have the sum of the n integers. And so this is just e to the minus n choose 2 times s, right? Or sorry, n times n plus 1 over, so it's n plus 1 choose 2. Okay. And as soon as this number gets bigger than 1, this quantity gets small, and it starts to decay exponentially fast. So as soon as n plus 1 choose 2 is significantly bigger than s, you're going to have a very small chance of having no collisions. Okay? So we're really stuck in our space-bound unless we have a clever idea or unless somebody else already had a clever idea. And they did. So I will now show you a paper by Itai, Komlosh, and Zemaretti. These are people that you rarely hear about in the algorithms community because they're actually more like complexity theorists, but sometimes complexity theorists are useful. Not all that often. They're usually busy proving lower bounds that stop us from doing what we want to do, so it's like the opposite of useful. But sometimes they give us upper bounds. And they introduced a really cool idea of two-level hashing. And the algorithm is very straightforward. What you do is you hash your n items to n buckets, or let me say order n in case I need some slack, to order n buckets using your favorite two universal hash family. So this is going to create collision. Yes, question?
Do you mean theta n buckets? Or omega?
Yes, sure. I mean, you're going to use at least n buckets because, but my point is, I think n buckets is fine, but I don't want to have to go back and fiddle with my constants, so I'm giving myself some slack. And so you use your favorite two universal hash family, and we already know this is going to cause collisions, right, with high likelihood. So what do? You build a two universal hash table, universal perfect hash table, in quadratic space on each bucket. So however many items land in a bucket, you allocate the square of that much space, and you use our quadratic space perfect hashing technique in each bucket. Okay? So this is not literally a perfect hash function, but it is still perfect hashing in the sense that you are guaranteed to have constant lookup time for each item. Now the constant is 2, right? In order to find an item, you have to hash it into the top level to find its bucket, and then you have to hash it into the hash table for that particular bucket, but that's just 2 hashes. Yes? So great, we have a constant time perfect hash function, but now it's not clear what the space is, right? How much space are we using? Well, the top level is no problem because we're using order n space at the top level of the hash function. But what about all of these second level hash tables? How much space do they take? Yes?
Quadratic in the number of collisions?
Exactly. It's quadratic, but that's a per bucket. Yeah. Sorry, it's quadratic in the number of items, not collisions, right? So the space that we need if an item has, if the kth bucket has bk items in it, then we're going to need sum of bk squared space for all of the second level hash tables together. Yes? So we need to analyze that quantity. Okay. Now I'm interested in, well, I won't put the expectations around it yet, but I claim that I can write this, right? This is the sum over k. What is bk? Well, it's the sum over all the items I of the indicator that I is in, this is bucket k. Right? But I have to square that. Yeah? Okay. This is a square of a sum. Let's expand it out. Okay? So now we have the sum over all k of the sum over all pairs I and j of the event that I is in bucket k times the event that j is in bucket k. Right? But let me be a little bit careful about this. Sorry, let me sort of tidy this up a little bit. right? This is literally over all pairs I and j, but that means there's an ij and also a swap of ij. And there's also cases where I is equal to j. So let me write this as, first of all, a sum over k of a sum over I of the event that I is in BK. Actually, one question. When you take a product of indicator variables, what are you doing? It's about a conjunction, right? They both have to happen. So I can write this as the sum over k, sum over ij, of the probability that I and j are both in BK. Right? So if I separate out the cases where I is equal to j, this is just the event that I itself is in BK. And then separately, I have a sum over all k, a sum over all pairs, I and j, of the event that, sorry, no probabilities here, these are indicator variables, of the event that I and j are both inside of BK. Right? Okay, let's analyze these. So here we are summing over all k, and now we're sort of totaling up the number of items that are in bucket k, right? So if I sum over all buckets, the number of items that are in bucket k, what do I get? Yeah. I get n, right? Every item is in exactly one bucket. So you can think of this as just sort of swapping the order of summation, right? If I sum over item I, and now I sum over all the indicator variable for all the buckets, the sum of those indicator variables for the bucket for item I is going to be 1. So this first term is n. Now can we apply the same kind of insight to the second term, right? If I sum over all buckets, and now I count the number of pairs of items that are both in bucket k, what am I actually counting? What if I swap the order of summation again? So I take a particular pair I and j, and now I sum over all k, the indicator of I and j both being in bucket k. Yes?
You're just counting collisions, right?
I'm just counting collisions, right? If I look at all of the buckets and ask, are I and j both in bucket k? If I look at that over all buckets, I'm asking if I and j are in the same bucket. That is, I'm asking if they collide. So the second term is just equal to the sum of the Cij's. Okay. Now, if I now put an expectation around all of this, what do I get? What's the expected value of the sum of all the Cij's? Yes?
N over S.
It's n squared over s. We already analyzed it to do our quadratic perfect hash function, right? So the expected space is just equal to n plus n squared over s, which is order n if s is equal to n. Right? So if we just make the top level hash table be of size n, then the total space of all of the second level hash tables is order n. And that means that the total space of the entire data structure is order n. So now we have the perfect hash function, pun intended, right? It uses order n space, and it gives us worst case constant time lookups for all of the items. Okay. Yes?
I had a question on the math on the second equation line.
Yes.
Why are there two terms? Why is it not just the right term? Why is the left term there?
Because because it's just a simplification for writing, right? If I is equal to j, then it's not really a pair anymore. It's just I, right? And the joint indicator variable is not that I and I are in bucket k. It's just that I is in bucket k. Okay? And we don't generally talk about I colliding with itself. I mean, you could define it that way, and you could do the analysis that way if you wanted to. Okay? All right. So that's perfect hashing. Again, what we've studied here, now some sort of postscripts on perfect hashing if there are no more questions. First of all, what we studied here assumes that you know the n items, and you're generating the perfect hash. Actually, sorry, before I postscript, how long does it take to generate this perfect hash function? Well, we use the Las Vegas technique that we just described above, right? You generate a perfect hash function for the top level, and you make sure that its sum of squares is order n. In expectation, it will be. And so by Markov's inequality, you have a 50% chance of getting a good top-level hash function. If you don't get a good top-level hash function, generate another one. And keep going until you have a good top-level hash function. Right? We already proved that this just takes a constant number of tries in expectation. Now you do the same for all the second-level buckets. And for each of them, you generate the appropriate hash function, and you may have to retry, but in expectation, only a constant number of times. So in expected linear time, you're able to generate this perfect hash function. You do need to have the items so that you can inspect and say, is it perfect? Okay, if it's not, I'll try again. Right? You can't generate the hash function before you know what the items are. Now this takes me to the first piece of the postscript, which is, what if you want to do insertions and deletions? Right? Now the set of items is changing, and so what was perfect might become imperfect. Okay? And so this is what's known as dynamic perfect hashing, and that will be on your problem set. Okay? How to deal with the basic idea, though, is just, well, when the function isn't perfect, just make a new one. And you just have to be a little careful to make sure that that doesn't take too long. Yes?
I have a question about, you said we'll move it into buckets, or
Yes.
m buckets at the first level, and then we'll do the perfect hashing thing. But then what's the value of x now, since all of them have the same index?
Sorry, ask that question again.
So if we have like 5 elements at box 1,
Yes.
and we need to do a perfect hashing for them,
Yes.
all of them have the value of 1, then how?
So thank you for the question. I should be clear that you use different hash functions at the second level. You don't just reuse the same hash function that you used at the top level.
Yeah, I mean, it's not the hash function, but it's the value of the item. So because there we use the value of x, which is the value of the item, but not all of them have the same value.
Well, they have the same hash value, right? So when I compute the top level hash function, it's going to put the same value for whatever 5 items, and so they're all going to end up in the same bucket, right? But now to create the second level of hashing for those 5 items, I pick a different hash function, and for that different hash function, the value of the hash will be different for those 5 items.
So this is, we can say it's a map for unique numbers, or what if we don't have unique numbers?
Oh yes, if you don't have uniqueness, then obviously you don't have perfection, because any 2 identical keys have to go to the same place. That's the definition of the hash function. Okay, so yes, this assumes unique keys. All right, one other little postscript. How much space does this take really? I was sloppy with my O's, right? Like I said, use O of n space for the top level, and or it's order n, that the sum of this stuff is order n. What is it really? So if you do this in the completely naive way, then if I remember correctly, I think the space usage is 13 times n in the original paper. If you're just a little bit careful, you can get the space usage down to like 6n or 5n or something like that. If you get really aggressive, you can get the space down to n plus little o of n. Okay, and this is measuring now in terms of the number of machine words that you need to store the hash function and all of the items, each of which is assumed to fit into a machine word. Okay, now in order to do this, you have to be very aggressive. Essentially, what they rely on is, obviously some of the buckets are going to have multiple items in them, and so you're going to need quadratic space for those. So how can you get away with n space? The answer is that in your top-level hash function, some of the buckets are going to be empty because you're randomly placing items in buckets, and you use the empty space in the top-level hash function to hold the second-order hash tables. Okay? Remember, these are complexity theorists. They do things that no self-respecting programmer would ever do, right? But, you also have to play with bits. Like you use some of the bits in the word for one thing and some of the bits in the word for another thing, and it gets very esoteric. And if you have fun with that sort of thing, you should go read the ITech Homotion Zemaretti paper. All right, that's the end of the story for perfect hashing, unless there are any final questions. Yes?
When you say like hash n items to like n buckets using the 2 universal family, do you ever like rerun this if you get a bad result?
Yes,
And
that's
then when-
exactly what you do. So I mean, again, you can take the Monte Carlo approach or the Las Vegas approach, right? You can say, I'll hash to n top-level buckets, and it's probably fine, and I'll just keep going, and if it's not fine, I won't care, right? Now, at the second level, you actually kind of need to use the Las Vegas approach because you're trying to generate lots and lots of hash tables, and so probably some of them won't work the first time.
How do you know like when it's bad though?
That's what I said about needing to have the items while you're constructing the hash table. So the way you check whether your hash function is good or not is you put all the items where they're supposed to go, and you see if there are too many of them in one place. Okay? Yes?
Wait, so like for the 13 end result that you just talked about, doesn't this highly depend on like when you choose, or like on, like there's like a space-time trade-off here, right? Like you can run it a bunch of times until the...
So that space-time trade-off doesn't gain you very much. That is, the 13n is how much space you need for your hash function to be perfect. And if you use that much space, then you find that hash function, that perfect hash function very quickly. You don't need to do a lot of tries. If you get down below 13n and you don't do anything clever, then it takes you a then you really don't have a chance of finding things through randomness. Okay, so yes, there is a space-time trade-off, but not one that really helps you. Okay? In order to get the space down, you have to instead change the way that you're representing the hash table. Okay. Any other questions? Okay. I didn't want to break in just before ending hash tables. Let's take a very short break, and I'll give you a quick intro to Maxflow before sending you away for the vacation. I guess we don't need a break, huh? Everybody just wants to keep going? No? All right. All right, let's get started. Our next big topic is Maxflow. Okay. okay? And you might be wondering, what could I possibly say in 10 minutes about max flow that would be worth squeezing into this lecture? And for most topics, nothing. But for max flow, I'm just going to define the problem, and that's going to be enough to let me give you lots of homework on max flow, okay? So actually, just a curiosity, how many people have seen max flow before? This number's been going up year by year. Okay, so as I expected, we're approaching 100%, right? What was that?
Let's define max flow as a problem of linear programming.
It is a linear programming problem. This is correct. And we'll get to linear programming. We're now entering the domain of combinatorial optimization, which will occupy a big part of this class. Okay? We were doing data structures where it was all about logarithmic terms and sort of, you know, basic operations. For the next month, we're going to be looking at problems where the problem is complex, and even knowing how to find a solution at all is tricky, but where there are polynomial time solutions. And the goal is to have the best polynomial. Later on, we'll look at problems where it's not even clear that there are polynomial solutions, and so we just want a polynomial. But for the next month, we're really going to be caring about exactly what the polynomial is. Okay. And so just to define the problem, we're given a graph G, which has a source S and a sink T. And we want to assign, and the edges have capacities denoted by U. Now, you might think I would use C, but it turns out that C is used for something different in combinatorial optimization, so we can't use it for capacities. We'll see C in a few weeks. And we want to find a flow which is a number that you assign to every edge, satisfying a number of constraints. The first is conservation, which says that for every vertex V, and this flow is going to be non-negative everywhere. And so what you want is that the sum of the flow from V to W on every edge, summed over every W, minus, that's the flow out of V, minus the sum of the flow into V is equal to 0, unless the vertex that you're measuring at is S or T. We have capacity constraints, which require that for every edge, the flow value is between 0 and the capacity. And if we have those two criteria, we say that the value of the flow is just the total amount of flow running out of S to any other vertex W minus the total flow running into vertex S from any vertex W. Okay. Now, in that formulation, all the flows are positive or non-negative, and you can actually have flow going from V to W on that edge, and also have flow going from W to V on the reverse edge. So there is an alternative, what you would call net flow formulation, where now you allow the flow to be negative, and instead you say that the flow satisfies the skew symmetry property, which says that F sub VW is equal to minus F sub WV. So now the flow just represents the difference in the amount of flow going from V to W and the flow going from W to V. So it's the net flow between V and W. And this forces you to slightly change the criteria for the flow. The conservation formulation now says simply that for every vertex, the sum of FVW is equal to 0, unless sum over W is equal to 0 unless the vertex is S or T. And also the capacity constraint no longer requires the flows to be non-negative. You just say that the flow on edge E is less than the capacity. But now again, you think about this in both directions, right? So obviously, if you have positive flow from V to W, then you're going to have negative flow from W to V, and so the capacity constraint will be trivially met in the W to V direction, but it is otherwise the same constraint. And we also changed the notion of the flow value to be that it's just the sum of the net flows out of V. So from a mathematical perspective, this net flow formulation is a little bit more elegant, or from a linear algebra perspective. But for thinking about algorithms, the gross flow, where all the flow values are positive, I find it much more intuitive. And so I'll generally be using the gross flow formulation to talk about the algorithms that we're developing. Okay? So what is sort of interesting, useful about the max flow problem is the insanely large number of real-world problems that can be formulated as max flow problems. So some of them are very obvious, like if you have a collection of pipes in your building and you want to push the most water possible from the inlet to the outlet, well, that's a max flow problem, okay? But for example, about 20 years ago, the admissions office contacted me about finding a better algorithm for assigning prefrosh to hosts in the dorms, and it turns out that that's also a max flow problem if you formulate it the right way. Okay, and this is why I'm doing this introduction. In your homework this week, you'll look at a few other problems that it's kind of surprising that they can be formulated as max flow problems, but they can. And so it's just a very general purpose sledgehammer for solving many problems that arise in practice, and therefore people want to have as efficient a sledgehammer as possible. They want to maximize the they want to minimize the time that it takes to solve these max flow problems. Okay? So that is what we will start doing next time. Next week will be devoted entirely to algorithms for max flow. Now I should say, I should warn, as I already did, Monday is Rosh Hashanah. I won't be in. And so instead, we will have the TAs here playing a recording of the lecture that I gave in a previous year. I encourage you to come because that way you can raise your hands and the TAs will stop the lecture and will answer any questions that you have about this introduction to max flow. Obviously, you can stay home and watch in your pajamas instead, but then you'll just have to hope that last year's students already asked the questions that you're going to ask when you see the lecture. Okay? Great. So I will see you on Wednesday. Have a good break on Friday.